Hello everybody. So in this video, we're going to solve some examples on natural response of RL circuits. Okay, so this is problem 7.2 from the textbook. So here's the given circuit. So it says this switch, now let's see, take this color, the switch here, oops, that's the wrong color, which I usually use. Okay, so this switch here is at position A for a long time. And at time t equal to 0, it switched to position B. Okay, so that is the situation. Now they're asking us, okay, for point A, determine the initial current in the inductor. Okay, so initially, so the switch was at position A, and it was switched to position B at time t equal to 0, right? So then the current through the inductor here, at time t equal to 0 will, because the inductor current cannot change instantaneously, it changes continuously, then it will be the current when at time t equal to 0, the current in the inductor will be what it used to be when the switch was at position A. Okay, so then I'm going to draw the circuit at position A. So this is 60 volts, 30 ohms, and another 90 ohms. And this is A here. And then I have the inductor. This is 0.32 Henry, like that. Okay, and they're asking us what is the current here. Okay, now note that they say the switch has been in position A for a long time. That means everything is settled down. Since the only source here is a DC source, that means after a long time, all currents and voltages will be DC currents and voltages. Okay, so that means, let me get rid of this. Okay, so that means the current through the inductor here is, the current through the inductor is DC current, right? If it's a DC current, voltage across the inductor is equal to L times the derivative of the current. And if the current is a DC current, then they should be equal to 0. So the voltage here is 0. Okay, so then I can do KVL in this loop and say, okay, I'm going to start at this point, come back to this point, and do clockwise. Okay, so let's do that. Sum of all voltage drops equal to 0. So negative 60. Whoa, I zoomed out way. Okay, so negative 60 plus 120 times I plus 0 is equal to 0. Right, 120 is the sum of voltage drops here and here. So this means I will be equal to 2 amperes. Right, that's problem A. Okay, I should probably zoom into 100% and write this. Okay, B, determine the time constant of the circuit for t greater than 0. Okay, so B, time constant for t greater than equal to 0. So let me draw the circuit for t greater than 0 and see how it looks like. So this is 70 ohms, this is 90 ohms, and the inductor 0.32 Henry. Okay, and this is how it looks like. So remember, for the time constant, we want to reduce the circuit to something like this, where this is the R equivalent and this is the inductor L. And then if you reduce the circuit to this form, then the time constant T would be equal to L over R. Okay, so then in this case, then if you reduce the prop circuit to this form, then your R equivalent will be equal to 160 ohms. Okay, so this means my time constant tau is equal to 0.32 Henry divided by 160, right? So this will be equal to 320 millihenry divided by 160. So this will be equal to 2 milliseconds. 60 ohm, 2 milliseconds. Okay, so that is my time constant for part B. So for part C, now they say find I, V1, and V2 for t greater than equal to 0. I, V1, V2 for t greater than equal to 0. Okay, so let me draw the circuit again and denote where V1 and V2 are. So this is 90 ohm and this is I. This is 70 ohm. This is V2 and this is the inductor. This is V1, 0.32 Henry. Okay, so I, V1 and V2. Okay, so we know the current through the inductor, right, I will be equal to I0 times e to the minus t over tau, right? So if this is the inductor, so and then I know I0 is equal to how much this we got as 2 amps, right? So that means for I, then we have 2 times e to the minus t over, let's say 2 milliseconds, right? T over 2 milliseconds. So this should be equal to 2 times e to the minus let's say 1000 over 2, 500 t. Okay, that is I. And then for V1 is the voltage across the inductor, and we know V1 of t. Now note that the voltage drop here is in the direction of the current I, right? So V1 of t will be equal to L times the derivative of this current. Let me denote this as I of t here. The same thing should be here, times I of t, and this I of t is the same as this I of t because it is in the direction of the voltage drop V1 of t. Okay, so this will be equal to inductor is 0.32 Henry, 0.32 times the derivative of the current. That will be equal to d by derivative of 2 e to the minus 500 t. So this should be equal to 0.32 times 2 times minus 500 times let's see, right, minus 500 times e to the minus 500 t. Okay, so minus, all right, so this would be minus 1000 times 300, so minus 320 times e to the minus 500 t. That is V1 of t. Okay, so what it says is now since the voltage is negative 320 times this thing, what it says is, let's see, so this point is at a higher potential than this point, right? So it is consistent with our intuition, at least if we build our intuition correctly. Since the current is going in this direction here, you can view the inductor as the power source driving that current in this direction through the resistors, right? And remember that only lasts for a very short time. So inductor is indeed acting like a power source, but only until the energy stored in it is dissipated, right? So the voltage drops off very fast, right? But for that brief moment here, even though there is no power source in the circuit, the inductor is acting like the power source, and the energy stored in the inductor is being dissipated into the resistors. Okay, so that's about part C, right? Now let's do part D. Okay, part D is asking us, okay, part D is asking us what percentage of the initial energy stored in the inductor is dissipated in the 90 ohm resistor. So I have the circuit again here. This is 70 ohm. This is 90 ohm. This is the inductor. This is 0.32 Henry. Okay, so initially there was 2 amps current here. And then they're asking what percentage of the energy stored in the inductor is dissipated in the 90 ohm resistor. Let's see, 1 millisecond after the switch is thrown from position A to position B. What percent of initial energy stored in inductor is dissipated? Okay, so for this we have to calculate the total energy stored in the inductor at time t equal to 0. And that is the energy which is being dissipated into the resistors, right? Then you have to calculate the energy dissipated in the 90 ohms until 1 milliseconds and look at what percentage of the total energy is that energy, right? So let's see, okay. So the energy So the energy in the 90 ohm resistor, so total energy dissipated until time t, right, will be equal to 0 to t, the power being dissipated in the resistor times dt, right? And that's basically that's from the definition of the power. So this would be equal to 0 to t. Power is I squared time of t times r, which is 90 here, times dt. So that should be equal to 90, 0 to 1 millisecond, I squared of t. So I is, we just saw I is 2 times e to the minus 500t, right? So if you put that here, that would be 4 times e to the minus 1 milli, like minus 1000 times t dt, right? So this should be equal to 90 times 4. Then if the antiderivative, there would be minus 1 milli on the denominator, e to the minus 1 milli t, applying limits from 0 to 1 millisecond. Okay, so this should be equal to, let's see, 360 negative times 10 power 3 times, let's see, this should be, okay, if you do that, 1 minus e to the minus, this is 1000. Oh, okay, this should not be minus 1, this should be minus 10 power 3. Okay, so if you substitute 1 millisecond for time, this should be equal to e power minus 1, right? So that's the energy. This should be joules. Let me see. So this was this should have been 1000 here, so this should be here to milli. Okay, so there, I made a mistake here, so let me let me redo this here. I'm going to start from right there, so that I want to redo this so that there is no confusion. All right, so once again, 0 to t, I squared would be 4 e to the minus 1000 t, okay, times dt. So this should be equal to 360 divided by 1000 times 1 minus e to the minus 1000 milliseconds, 1 millisecond. Okay, and this limit here is 1 millisecond. Okay, so this should be equal to 0.36 times 1 minus e to the minus 1. Okay, so that's the energy stored, energy dissipated in the 90 ohm resistor until 1 millisecond. Okay, and then the total energy stored in the inductor is half L I0 squared at time t equal to 0. So that should be equal to half 0.36 times I0 was 2, so that's 4 amps. So this is 2 times 0.36. So the percentage of the energy dissipated in the 90 ohm resistor would be E90 at 1 millisecond divided by the total energy stored in the inductor times 100. So this should be equal to 0.36 times 1 minus e to the minus 1 divided by 2 times 0.36 times 100. So, and then I have to calculate this. Great, my computer got into lockdown. So 1 minus e to the power minus 1 divided by 2. So that will be 31.6%. And that's, so now let's look at problem 7.18. in the textbook again. So we have a slightly more complicated situation here. As usual, again, we have a one circuit to establish initial conditions, another circuit to look at natural response. So they say for time t less than 0, the switch here is position A, and it's at that position for a long time. That means until things settle down. And then at time t equal to 0, it's moved to switch position B. And then they're asking us to, they have some questions on basically based on natural response. Okay. So let's look at the condition when the switch is at position A for t less than 0 and for a long time. So for t less than 0, I'm going to draw the circuit here. So I have, okay, I think I can look at the textbook. So we have 12 amps, and I have a 150 ohm resistor here, a 30 ohm resistor here, and then I have the 8 millihenry inductor. So this is for t less than 0, and let's say in stable conditions there is a current I0 flowing through 8 milliamps. Okay, so under stable, since this source here is DC, under stable conditions all currents and voltages are DC. Okay, so that means if it's DC, that means I0 is a DC current. If it's a DC current, the voltage drop across the inductor is 0. So it's basically, if the voltage drop across this is 0, it's just acting like a simple wire, so like a short, right? So that means this 150 and 30 ohm resistor are in parallel. So that means using the current divider rule, I can say I0 should be equal to 150 divided by 180 times 12. So this will be 5 over 6 times 12. This should be equal to 10 amps. So now I have the initial conditions. So once the switch is moved to position B at t equal to 0, I'm going to draw just the new circuit in that position and label the circuit with initial conditions. Okay, so let's see. So I have a 8 millihenry inductor here, and then I'm going to rearrange the circuit a little bit. So as to say 2 millihenry here, and then the 8 ohm resistor here. All right, and so just as that switch is closed, there will be 10 amps of current going through here. There will be no current here, and there will be no current here. Just when the switch is this current has to go there, right? So just when the switch is just before the switch is being moved to the new position, there was no current through the inductor 2 millihenry, right? So that means since the current in the inductor is continuous, it still remains 0. But then according to KCL, then at this point, then the current here should also be 10 amps. Then that current will be going through the resistor here. Just a sec. Okay, so now in order to do natural response analysis, I want to reduce the circuit in this form where there is a inductor and there is a resistor in parallel, right? So here I only have one resistor, so it will be 8 ohms, and I have two resistors in parallel, two inductors in parallel, so that will be 8 times 2 divided by 10, 5, so that will be 1.6 millihenry, and the initial condition here is 10 amps. Okay, so then my time constant is L over R, which will be equal to 1.6 millihenry divided by 8 ohms. So this will be equal to 2.2 milliseconds. That's my time constant. Okay. So now they're asking for I0 of t. So I0 of t, IO, and IO as labeled in the circuit is in this direction here. All right. So IO should be equal to I0 times e to the minus t over tau. And I0, according to the direction of I0 should be minus 10, right? So then IO of t is equal to negative 10 times e to the minus t over tau. So that's part A. Okay. So now part B is what is the total energy delivered to the 8 ohm resistor. Okay, so I want energy delivered to the 8 ohm resistor at, because it's the total energy, that means I have to wait until infinity to calculate the total energy. So it will be 0 to infinity IO squared of t times R dt. Okay, so this should be R times 0 to infinity. IO is I0 times e to the minus tau of t. So that should be equal to IO squared times e to the minus 2 t over tau times R dt. Oops, I already took R outside, so this shouldn't be here. So then this will be equal to R IO squared. I'm getting IO squared out. And the integral of that would be tau over 2 times 1 minus e to the minus infinity, right? So this will be equal to R tau over 2 times IO squared. This is E8 of infinity. Okay, let me put this as a formula, and then I can plug in the values to get 8 times tau was how much? 2 milliseconds? 0.2 milliseconds. It was 0.2 milliseconds divided by 2, and IO is 10, so 100. Okay, so this will be 0.1. Well, 0.2 milliseconds, right? So 10 power minus 32. So this is 100 times 10 power minus 4, 8 times 10 power minus 4 joules. So 8 times 10 power, 10 power minus 2 joules. So this should be equal to 80 millijoules, right? So that's the answer, but that's the formula over there, and then you plug in. Okay, so that's B. And now C is asking how many time constants does it take? So T over tau is equal to how much to deliver 95% of the energy, 95% of the energy found in B. That means I want the energy at time t divided by the energy at total. I want this to be equal to 0.95. Okay, and then what should be this ratio when this ratio is equal to 0.95? So let's look at that. So if you look at this integral here, well, let me do that again. It's not a big deal. So E8 of t should be equal to 0 to t IO squared of t R dt, right? So this would be equal to 0 to t capital IO squared times e power minus 2 t over tau times R dt. So this should be equal to R IO squared, and then this integral will be tau over 2 times 1 minus e power minus 2 t over tau. Okay, and this is E8 of t. And if you remember from above, E8 of infinity will be equal to R IO squared tau over 2. So this means E8 of t divided by E8 of infinity is equal to, so this here and this here cancels out. So this means 1 minus e to the minus 2 t over tau. And we are given that this should be equal to 0.95. This means e to the minus 2t over tau will be equal to 0.05. This means 2t over tau will be equal to negative ln 0.05, and we want t over tau. So this means t over tau should be equal to minus half ln 0.05. So open Google, minus 0.5 times ln 0.05. This is equal to 1.497, so approximately equal to 1.5, right? So what this means is, if you look at the inductor discharging here, let's say, if you go to this circuit here, right? If you look at the inductor discharging equation, we know the current, the current is never zero, right? It's always going on until infinity. But if you look at this equation here, this current never reaches zero, but it will exponentially drop off. But now if you look at this answer, what they're saying is, even though the inductor never completely discharges, let's go down, right? Just after 1.5 time constants, it will discharge 95% of its energy, right? So even though the current is continuously flowing for infinity, just after zero point 0.4 milliseconds, it lost 95% of its energy, right? So that's why the time constant is so important, because it will give you, like approximately when the inductor will be completely discharged, right? So here, after, if you just wait 1.5 time constants, you can say inductor is pretty much all discharged, right? So that's what you want to take away from this problem.